Okay, so yesterday we kind of did a review of ionic bonds. Today we're kind of doing a review of covalent bonds. We are heading up on almost being done this unit. We're almost at the review point. So I think our test will be next Tuesday. Are we okay with that? It is the first day back after the break, but are we all right with that? Tuesday? Okay. So test on unit 3 next Tuesday. So that'll be Tuesday, April, today is the 15th, 1 week from today, 15 plus 7 is the 22nd. Okay? Okay, so if you recall, sometimes we have, when we're doing, and this is covalent bonding, tell your partner the difference between covalent bonding and ionic bonding. Okay, what is one thing that's different? Yes. Okay, so I think I heard you. I'm interpreting because you're at the back of the room and this fan is blowing and it's kind of hard to hear. Did you say that covalent bonding is with nonmetals? Good, excellent. And ionic bonding is metal plus non-metal. What is another difference between the two of those? Yes, you can borrow a pencil. And while we're borrowing a pencil, what is another difference between ionic and covalent? Has to do with the electrons. In which one are they shared? In ionic? They're not shared in ionic, they're actually shared in covalent. Okay, so in covalent, the electrons are shared. What happens in ionic? Yes. Yep, metals give. Metals are given and taken. All right, and yesterday we focused in on ionic bonding. Today we're going to refocus in again on covalent bonding. And we are going to look at multiple bonds here. Like I said, if you are doing the enriched stuff, this is what a dot and cross diagram looks like. The reason that we've drawn the electrons as dots in one atom and crosses in the other atom is so that you can tell which electrons came from which atom. And with fluorine, how many gaps does fluorine have in its outer shell? 1. So they can share 1 electron each. Okay, and that is called, what type of bond is that called? That is a single bond. How many electrons is a single bond? 2 electrons. Okay, and it's represented by 1 line. we have here, instead of fluorine now, we now have an oxygen atom plus a second oxygen atom. And you'll notice in this one, what did we do with the inner shells of electrons? We just ignored like there would be a shell in here with a couple of electrons on it, and we're just ignoring it. Because when atoms bond, they always bond with their outer electrons. So you don't really have to draw the inner ones. If you know that oxygen has 6 valence electrons, you can just draw 6 in the outer shell. How many gaps in oxygen? 2 gaps. And if you have 2 gaps, how many bonds do you form? 2 bonds. Yep. Two gaps. 2 bonds. So what'll happen is we will have these 2 guys getting together here, and then we'll have those 2 guys getting together down there. All right, and now we have that sharing there, and we have that one sharing, oops, there. And this one is a double bond. How many electrons in a double bond? 4 electrons. And we show it with 2 lines. An oxygen atom and an oxygen atom to get together, and they form an oxygen molecule. A nitrogen atom and a nitrogen atom get together and they form a nitrogen molecule. And there is a lot of sharing going on in this nitrogen molecule because we have 1, 2, 3 gaps. 1, 2, 3 gaps. Therefore, there's going to be 3 bonds. All right, and we're going to have 1 bond where these 2 guys get shared, 1 bond where these 2 guys get shared, and then 1 bond where these 2 guys get shared. And so we have 1, 2, 3, 4, 5, 6 shared electrons. And 6 electrons is a triple bond. Which bond do you think is the strongest out of fluorine and oxygen and nitrogen? Nitrogen is the strongest. It's got the most electrons pulling the 2 nuclei together. So this is the strongest. This is the weakest. And of course, oxygen is in the middle. double bond is in the middle. Middle strength. You can almost think of it like there's ropes holding them together, and fluorine has one rope, right? And oxygen has two ropes, and nitrogen has three ropes. The one that has three ropes holding it together is going to be the strongest. Now, this next little bit is the actual explanation of why, rather than going into ropes. And this is enriched. So if you're like feeling a little tired and you're like, I don't really want to listen to this, you can just have a rest right now. Okay, but if you're interested, the strength of the electrostatic attraction, do you guys remember that word? Electrostatic attraction, that is the attraction between positive and negative charges. And how strong that attraction is going to depend on how much charge you have. Okay? And this is an example of a direct relationship. Do you guys remember that term? Did we go over that term? Oh, it's a positive relationship. Positive. Correlation. So basically, as the electrostatic attraction, as the amount of charge increases, the electrostatic attraction increases. Oops. As charge increases, electrostatic attraction, that's such a big word, increases. So if you're like, what's going on there? Well, if we have fluorine, it's got, this is our nucleus. And in between, we have positive being attracted to this negative charge and positive being attracted to this negative charge. We have our nucleus on the other side attracted to one electron and attracted to two electrons. Now, if we have, instead of just one pair of electrons, by the way, if we have one pair of electrons, what type of bond do we call that? One pair of electrons is a single bond. Here we have two pairs of electrons, which means that we have a what kind of bond? Double bond. And you can see we have 4 electrons in here. Each of them has a negative charge. So it's like instead of having 2 magnets sticking these things together, we have 4 magnets sticking them together. Okay, because electrical force is very much like a magnetic force. Okay, so here we go. We've got attraction between the nucleus and electron 1, nucleus electron 2, nucleus electron 3, and nucleus electron 4. Those right there are our, can I just start calling it the ES attraction? And that stands for electrostatic. Okay, and then we have on obviously the same thing on the other side. So is that making sense why that is a stronger bond? Okay. And you could go as far and you could say, okay, well, what if I have 6? It just becomes bigger yet. Okay, and I haven't shown that one here because it gets hard to draw, but it would be closer yet. And you'll notice that this distance is longer. And the distance here is shorter. So a single bond is longer and weaker. A double bond is shorter and stronger. Okay. We're going to ignore this. If you want to read it, you can. There's actually attractive and repulsive forces, but we're just going to ignore that. This is going to be like a double black diamond. If you want to read it on your own, you can. All right. Once again, this is a little enriched bit here. Covalent network solids, not molecules. Now, normally, when things covalently bond, what kind of particle do we get? We usually get a molecule. Covalent bonding usually makes molecules. Molecules? What is happening with me? Molecules. Molecules. But every once in a while, especially when you have something like carbon involved, because if we remember carbon, how many valence electrons does carbon have? It is in group 14. Carbon is group 14. It has 4 valence electrons. Okay, so it looks like this. 1, 2, 3, 4. How many gaps does that give carbon? It has 1, 2, 3, 4 gaps, which means it can form 4 bonds, which means it can form, instead of just like when you have oxygen and hydrogen, say for example, like oxygen just has 1 gap, hydrogen just has 1 gap, so we can only really form like 1 bond in each direction, and we can't form a big network. But carbon, if you imagine that you are a carbon atom, your head would be one place to bond, each arm would be one place to bond, and your feet would be one place to bond. Okay, so you could form 4 bonds, and you can imagine you could like make a big, big network out of that. So we can have a network of carbon atoms where each carbon is bonded to 4 other carbons. And that makes diamond. Okay, so this is, this is a very, very valuable model here. It's pure diamond. Yeah. All right. But that's one of the reasons why diamond is a crystal shape, is because it is almost like a crystal lattice. Yeah. Okay. So that is our diamond. And because covalent bonds are really strong and everybody is stuck to each other with covalent bonds, that makes diamond super strong and super hard. Okay. So diamond is one of the strongest, hardest substances. So covalent bonds, very strong. Therefore, covalent networks are very strong and very hard. Silicon dioxide, that's like sand. Silicon carbide is another kind. And we actually have a 3D model of another form of carbon. And this one is the kind of carbon called graphite. Do you guys know where you would find graphite? In your pencil, yes. Now, you might think to yourself, hang on, Ms. Spence, you just told me that these covalent networks are very, very strong, and yet my pencil can break. So, part of that is because if we look at this structure, do you see how it makes almost like a honeycomb shape? We've got hexagons there. Yeah. Each little sheet of hexagons is held together by covalent bonds. So each carbon is bonded to 1, 2, 3 other carbons. Okay. Now, because this is a model, I can't just have these floating separate from each other. There actually has to be something to attach them. But these right here, have we talked about intermolecular forces in this class? Maybe, maybe not. Okay, we'll talk about them again. So intermolecular forces, covalent bonds are very strong. Do you guys know what the prefix inter means? Inter actually means between. So if you go on an international flight, you are traveling between nations. So inter means between. And so there is, although all the atoms in a covalent network solid are bonded to all their neighbors by those very strong covalent bonds, we also, in graphite, have another type of force called an intermolecular force. So knowing that inter means between, we could define an intermolecular force as being a force Anyone want to take a guess at how to end that sentence? What does inter mean? Between. So it is a force between what? Molecules. Now, to be honest with you, we use intermolecular forces also to mean forces between atoms if they're not actually bonded to one another. we use intermolecular forces to mean the attractive force between one sheet of graphite and the next sheet of graphite. Okay? And intermolecular forces are relatively weak. Okay, intermolecular forces are relatively weak. So, within our little hexagon, strong, 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 strong within the layer. But between the layers, these are actually very weak. Okay? And let's say my desk was a sheet of paper. Say my desk is a sheet of paper. So there are intermolecular forces in between this sheet of the graphite and the second sheet of the graphite. But when I touch the pencil to the paper, if we pretend my desk is the paper, there will also be intermolecular forces between the graphite and the paper. So what will happen is if we press down, those will be quite strong forces, and it will actually cause these intermolecular forces to break. This layer will shear off and be left on the paper. Okay, so it's quite cool. And you can actually see that. Here, graphite. You can see the different layers, and in between the layers of the graphite, we have these weak intermolecular forces. And if you get tired of saying intermolecular forces, you can say IMFs. Intermolecular forces are IMFs. Okie dokie. And then here we're just showing our graphite, and you can see here we have the IMFs. And just so we remember what it's called, they're called intermolecular forces. Do you know where else we learned the word? We learned inter. Do you guys remember learning inter earlier in the year? Yeah, when we interpolate. That is where we have our graphing. Our data is between the points, and extrapolate is beyond the points. You'll see all kinds of words like this in science where you have inter meaning between. Okay, so in biology, you'll hear interstitial, which I think means between cells or something like that. Anyway, all right. I'll let you think about question 1 and question 2. And I think what we could do is, why don't we work on the particle review? Because you've listened to me yak for long enough, maybe. Do you want me to go through it with you, or do you want to do it on your own? What do you think? Okay, this is on page 65. And hopefully, by this point, we have talked a lot about the 4 types of particles. We have atoms, we have molecules, we have ions, and we have formula units. Are we good with those 4? Yes. Okay. Do atoms have a charge, or are they neutral? Atoms are neutral. Yes. Mm-hmm. Molecules, do they have a charge, or are they neutral? Neutral. Ions, do they have a charge or are they neutral? They have a charge. And how about a formula unit? Does it have a charge or is it neutral? It's neutral, but it's made up of charged particles. Do we all know where the metals and nonmetals are on the periodic table? Yes? Who's the one who doesn't belong where it's supposed to be? Hydrogen. Hydrogen is a nonmetal, but it is on the left-hand side of the periodic table. Okay. Whoops, sorry. We good? Okay. Metals. Metals are usually, actually, metals, what does this look like? What does that almost look like? Looks like a sugar cube. Also looks a bit like it also looks like a crystal lattice, and that's because it's not an ionic crystal lattice. It's not made of positives and negatives, but it is a metallic crystal lattice. Okay, and it just consists of metal atoms tightly packed. They're tightly packed in an organized fashion. There's an exception, though. Who is the one element that is not, the one metal that is not solid at room temperature? Do you guys remember? Which metal is not a solid? Yes, mercury. Yeah. Okay, mercury is a liquid. So this is Hg, is the symbol for mercury, and it is a liquid, if you remember that little symbol for liquid. And the liquid is tightly packed but disorganized and mobile. What does it mean to be mobile? They can move. We also have nonmetals. And if you see a nonmetal that looks like this, that's going to be a noble gas. Why are noble gases the only nonmetals that are atomic gases, that are gases made of atoms? Why are noble gases atoms? Because they have that full outer shell, which means they're stable and they don't want to bond. Full outer shell makes them stable, therefore they don't bond. Okay. Whoops, where'd it go? Ah! Okay. All right, on to our next page. We have molecules. Molecules are neutral. They're made of only nonmetals. So they're neutral. They're made of only nonmetals. They are made of 2 or more atoms, and those atoms are bonded covalently. You can have molecules that are elements, and you can have molecules that are compounds. But all of them are going to be made of nonmetals. And they're bonded covalently. What are they doing with their electrons if they're bonded covalently? They are sharing their electrons, yeah. Well, that's a good stretch. Should do that more often. So here are a bunch of pictures of molecules. Let's look at them. We have some molecules of elements. Here's I2. Right here, this little stick, that is our covalent bond. And what is a covalent bond? It is shared electrons. How many How many electrons are in that bond? 2 electrons, yep. Okay, here is, and that is I2. Here we have, oh, this one's complicated. We don't very often get a structure like this. This is a weird little structure. This is P4. Okay, and P4 has lots of covalent bonds and it makes a little pyramid, which is kind of cool. Okay, and all of those are single bonds. Here's sulfur. Sulfur almost makes like a little crown. Sulfur is yellow, so it almost looks like gold, and it makes like a little crown, and there's 8 sulfur atoms in that, so that is S8. Here we have oxygen. What type of bond is that? That is a double bond. How many electrons? 4 electrons. All right. So those ones are all molecules of elements because the atoms are the same. And therefore that's an element. We can also have molecules of compounds. Here's a really complicated one. C8H10O2N4. Holy mackerel. How many atoms is that in total? C8H10, that's 18, plus 2 is 20, and then 4 is 24. 24 atoms. This one, I believe, is caffeine. Yep. I think that's a caffeine molecule. I could be wrong, but I think that's what it is. Okay. Now, we can get into things that are a little less crazy than caffeine. We have CH4. We did learn the name of this one earlier. Does anyone remember what CH4 is named? Yeah? No, you're close. Ammonia. Do we have ammonia on here? No, we don't. But if we had an N, H, NH3, that one is ammonia. CH4 is methane. And if you remember, carbon had 4 valence electrons, so it's got 4 gaps, so it can attach to 4 hydrogens. Nitrogen has 5 valence electrons, so it only has 3 gaps, so it can only attach to 3 hydrogens. Okay, so we have methane and ammonia. Those are names that if you want to learn them for the enriched part, you can do so. Okay, otherwise you just need to be able to say CH4 has 1 carbon and 4 hydrogens. It's made of 2 nonmetals, so it will be a covalent compound. And of course, then there's water. Oxygen has 6 valence electrons, so it only has 2 gaps, so it can only accommodate 2 hydrogens. Okay. And then, of course, there's our crazy old caffeine molecule down at the bottom. And because these are made of a stick in between a ball and a ball, we call these ball and stick models, because they're made of balls and sticks. There we are. Ball and stick model. There is another way of showing molecules where we don't actually show the covalent bonds as sticks. We just show the atoms overlapping each other. This is more accurate, but it can also be more confusing because everything starts to just get all like smooshed up, right? These are called space filling models. And you can see here's O2, S8, H2O. It's really harder to picture what's actually happening in terms of the bonds. Plus, it's also harder to sort of imagine S8 being a little crown. You know, it's a little bit more difficult. Ions have an electrical charge. We did this yesterday. You can have monatomic ions. How many atoms do monatomic ions have? 1. We are now on page 67. 67. We have polyatomic ions, which have 2 or more, in other words, many. Yeah. Many atoms. Cat ions, if you remember, CAT has a plus sign in it. Cat ions are positive. Anions are negative. We got that N in there. Anions are negative. And you can have polyatomic, monatomic cations and anions. Cats have pos, anions are negative. These are what pictures of ions look like. They will always have a charge. Ions always have a charge. So if we look, sodium has a plus. We might write the plus on the inside, or we might write the plus on the outside. It doesn't matter. We can show it inside the atom or beside the atom. Over on the right-hand side, we have Cl with a little minus in it. Okay, and we can also write the charge on the outside, O2 minus. Here are some polyatomic ions. You can notice we have many atoms. Poly meaning many. And here we have a ball and stick model of ammonium. Ammonium is NH4. But do you remember with Bohr models what we did when it had a charge? We put brackets around it, square brackets. And we put the charge on the outside. And we do the same thing with models of a polyatomic ion. So you'll still see the charge though. Okay, we still see the charge. And if you see that charge, it is an ion. That one's ammonium.
Can I please go on?
Sure thing. That one's hydroxide. OH minus. We see the charge, the charge, the charge, the charge. So in terms of recognizing particles, if you see that charge, you know it's an ion. Formula units. It is a single neutral unit of an ionic compound. Usually we have our ionic crystal lattice. So this is now on page 68. Alternating positive and negative. We go from having the 3D structure to having a single slice to taking a single unit, and that is a formula unit. A formula unit will have both positive and negative charges in it. But overall, it is going to be neutral. So if you have a 1 plus and a 1 plus and a 1 minus, overall it's neutral. I think I used this with my grade 11s, so I expected them to be able to see that this is an ionic compound, but I would label these like plus minus for you because I think it's too hard. And you might get it confused with a homogeneous mixture. Yeah? So let's not have that happen. Okay. So the formula unit will always have charges. Ooh, but I'm going to show you something. Maybe you have a sulfide 2 minus and an Li plus and an Li plus. That is also a formula unit. It's made of positive and negative. Li plus and Li plus. How much positive charge does that give you all together? That gives you plus 2, which balances out the minus 2. So we have a positive 2 and we have a minus 2. So overall, the whole thing is neutral. Okay. And now we have some questions. So you guys have worked super hard. If you would like to take a little 5-minute break and we go around the parking lot and then we come back and do some work. Does that sound like a plan? Okay, let's go out, go around the parking lot because it's nice again today. All right. If you don't want to go around the parking lot, you can just go outside and do some like little stretches and enjoy the sunshine. Okay. You don't want to go outside? It's just beautiful out. You don't always get the sun here, so let's enjoy it while we have it.
Yeah, you can see it. Oh, where he's safe. He's sleeping right now. Go outside. Yeah, tell him that. Yeah. Brian's little pickup. Shut up, bitch. Oh, shut up. Shut up. Wait, so you're playing Snake 2 years in a row? Yeah. Down. Okay. You're an experienced Snake now. I don't know. Put those lights on.
How about pages 69 and 70? You might even be able to finish it in class. Okay, we got a good 15 minutes almost. So give that a try. I'm just going to run to the washroom really quick because it was busy at break time. Hi. Okay, so yeah, basically it's different atoms. It's just a circle. Okay, right? And then now these are molecules. Two or three or four or whatever. Yeah. Ion is one of the ones that has charge. Sure. Ion. Sure, yeah, I'll call you in. Yeah.
When you say ground, what is it?
Yeah. They're always in a group, right?
Компьютер не лагал постоянно, я тогда был не. Я Тима хуя знаю, а хуя не знаю. Я знаю, что ты сделал. А ты как это сделаешь с этим?
In isolation. Okay, so that would be a formulated an ion because the whole part goes through this. How you doing? Great, you good? Yeah, and how are you doing? Yes. 69 and 70. Yeah. Perfect. Yeah.
Ну как хорошо.
Ion, is that neutral? Positive. If I do this, neutral. Is this one neutral? Neutral. Oh my God, it's wrong with you. Why? Can't have nice things. Wow. Like they're metal chairs. How do people manage to break? Grumpy. Nice things in the classroom, you break them. But I will this. Yes. I want to drop it for this to happen. Only it happens. Yes. Hmm? Yes. Otherwise? You sure? I don't know. What would you else? Oh.
Exactly what else? Oh, so.
The sun is happening. All right. I'm not worried. I don't know. Yeah, us. Hi, Fernando.
One thing I was curious,
Yes.
how is it? So, carbons have 4 valence electrons,
Mm-hmm.
so they can form
Uh-huh.
but graphite
Mm.
each only has 3. How is this?
Okay, so what actually happens here is that you end up having a double bond here, and a double bond here, and a double bond here.
Ooh.
But it gets even better than that, because what happens is the double bond will actually move to here, which kicks this one out and makes it move to there, which kicks this one out and makes it move to there. But it gets even better because really it's not kicking it out. The electrons get delocalized. They're actually spread out over all 6 of these. So you essentially have a 1.5 bond because the 2 electrons are kind of smeared out over this section, right? Yeah, it's pretty wild.
Damn.
And it is those delocalized electrons, and they actually like exist kind of above and below the plane. And that is what conducts electricity in graphite, because you have these mobile electrons that can move here, and they can actually move throughout the whole sheet. Yeah, it's pretty cool. That was a very, very good question.
It can conduct electricity, but it like
It only
it's
conducts
not really
electricity
efficient,
in
is
one
it?
direction. Right? So these delocalized bonds are here. So it'll conduct electricity in the plane of the graphite sheets, but it will not conduct electricity this way.
Yeah. And why is it that sulfur forms their way like not like an
That's a good question. I don't really know, to be honest.
like-
I'm like, why? Why are you doing that, sulfur? Why not just S2? Why not? I don't know. Yeah. Why are you so strange, sulfur? We don't know.
Not doing like the
Yeah.
when I see like the this one,
Oh, yeah.
it's symbols like this.
Yep.
Why is like there's a hydrogen? Why is it couldn't put it
Oh, why
inside?
is it not put with the other ones?
Yeah.
Okay, so alcohols, which are compounds that end in the name in all, let me just pause this thing here.